Hi guys, I would like to welcome each and every one of us to my channel of Honesty Sciences and Mathematics TV channel. I'd like to request us to kindly subscribe to our channel and engage us in the comment section so that we can be able to discuss on these various topics and assist one another in improving our skills both in mathematics, physics, chemistry and biology. So today we're going to look at the concepts of vector, differential operator, and particularly we're going to look at one of its applications in the concept of divergence. And earlier on in our previous video, we had looked at the concept of del, and we have we said that del is a notation that is going to be used, of course, given using this particular inverted triangle, and therefore we gave one of the derivatives of this, of course, del, which was referred to as a gradient, and we said that a gradient can be given as del phi, where phi we say is a scalar quantity which is going to be defined and differentiable at a region in space. And this, therefore we say that this specific concept of del, then therefore is going to be a scalar quantity which can be represented as this, which is a point in a region in space. And therefore we say that we can be able to give the gradient of phi using this combination of del phi. So let me give it as such. So hope it's del phi, and this del phi we say that can be given as d over dx phi I plus d over dy phi j plus d over dz phi k, which are vector fields as such. So this is going to give us what we refer to as a vector field, which is going to be defined as a gradient. And in this specific discussion, we're going to look at the second bit of application of this specific concept that we refer to as vector differential operator. And this is going to be what we refer to as a divergence. So therefore, in one of its areas of application that we had said, this concept of a divergence can be used to evaluate what we refer to as a volume integral, especially in the electromagnetic theory. So in this case, I'm just going to use an arbitrary point, like the first case that we had used for the description of a gradient. And therefore, we are going to have this particular function of this v represented as x, y, and z, which is a point in space. And therefore, this is going to be a point that is a differentiable, rather a point that is defined and differentiable. And then we are going to have this specific point, which is going to be defined and differentiable, which is going to make a vector field. Just write a vector field. And this is the one that we're going to consider whenever we are going to define this second case for our application of a del, which is going to be referred to as divergence. So the divergence of v, therefore, is going to be represented as del dot v, whereby, as we said, this one can be illustrated as d over dx I plus d over dx, sorry for this, y, j plus d over dy. This is dz, k, and these are vectors indicated as I, j, and k. So this is going to be dot v, and we've said that this particular v, of course, is going to be represented as these specific initials for the x, y, and z. And this, of course, as a vector quantity, as I said, is going to be given in terms of v can be given as v1 I plus v2 j plus v3 k, which is going to be given as such. So we have said that this also vector field is differentiable and defined. So the specific product that is going to define the divergence of this particular v, then therefore can be given using these various components that we have listed for v, whereby we're going to have v1 I plus v2 j plus v3 k given as such. So these are vectors of ij and k as I had mentioned. So the product of this we had done in one of the representation of vectors said about this concept of this specific elements. So this is equivalent to jj is equivalent to ji dot I is equivalent to k dot k, which is going to be unity. So therefore, if we were trying to evaluate this one, then therefore this is going to give us what we refer to as a scalar quantity, which is going to be represented as dv1 over dx plus dv2 over dy plus dv3 over dz, given as this. So this particular case for the definition of a divergence, then therefore is going to be a scalar field, unlike the first one that we had seen for the del phi, which was defining gradient, which was a vector field. So that's one of the elaborate difference between the two for divergence and gradient for the two vectors. One is a vector field, which is a gradient, and the divergence is a scalar field, which you can be able to indicate using this specific formula that I've given on the board. So this is going to assist us, of course, in trying to, as I said earlier, of course, do some calculations in its areas of application. And we had done one of the examples of this particular case in one of the videos that I'm going to put a link in the description box, so that we can be able to use it in combination with this one to understand this specific concept of divergence. So catch us in our other video where we're going to look at the concept of a curl, and that is going to form the last part of it, of course, but not the least of this specific discussion on the concept of vector differential operator. And we're going to see that the formulation of del is going to be used in combination with the other areas in order to define some areas like the diagonal of a curl of 0 and other areas like the curl of a gradient, and some of the areas of application like the Laplacian differential operator that we're going to see later in other areas of application. So that is it for now, guys. Catch us in our next video.